Hi everyone, this is Yan again. In Chapter 8, we'll learn about one-sampled t-test, which is very similar to z-test, so it should be easy. In Chapter 5, the foundations of hypothesis testing, we first introduced the z-transformation when we convert any normal distribution to a standard normal distribution. To compute the z-transformation, we use this formula for a population of scores, and we use this one for a sample of scores. In Chapter 6, we learned about sampling distribution. Sampling distribution is approximately normal, so we can convert a sampling distribution to a z-transformation. And in sampling distribution, the standard deviation is called standard error of the mean, and it is the denominator in this formula. Mean of the sampling distribution equals the population mean, so we can substitute the mean of the sampling distribution with the population mean. If we know the population variance, sigma, we can use this formula to calculate the standard error of the mean. But usually, we don't know the population variance, so we use the sample standard deviation to calculate the standard error of the mean. We can also use SPSS to estimate this standard error of the mean if we have a sample of scores. In Chapter 7, hypothesis testing, we use one sample z-test to test significance. In one sample z-test, we know the population mean, and then we know the population variance. Here's the population variance. So we can calculate the population standard deviation, and then use this population standard deviation to calculate the standard error of the mean. And then we compute the obtained z-statistic using sample mean minus population mean divided by standard error of the mean. This is the obtained z-statistic. This is the rejection region, which is set by the critical value of z, the z critical value. So if the obtained z-statistic falls into this rejection region, we reject the null hypothesis and conclude that there is a significant effect between the sample mean and the population mean. Then we'll use Cohen's d to compute the effect size. But in reality, we usually don't know the population variance. So we use the sample variance to compute the sample standard deviation, and then use sample standard deviation to estimate standard error of the mean. And because this estimated standard error of the mean, but the t-distribution is computed using the sample standard deviation, the sample variance, the degrees of freedom for t-distribution is the same as the sample variance, is n-1. The 4 steps in one sample t-test is similar to that in one sample z-test, except that we use the table of critical values for t-distribution instead of a unit normal table. And we call the standard error of the mean estimated standard error of the mean. And then we call the effect size estimated Cohen's d. I used the same bell curve for both t-test and z-test, but this is not accurate. T-distribution actually looks a little different. This is the figure 8.1 in our text. The blue curve is the standard normal distribution, and the 2 red ones are t-distributions. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. And T distribution is a theoretical probability distribution. It is symmetrical and bell-shaped and similar to the standard normal distribution. But it is different in that it has additional parameter, degrees of freedom, which changes its shape. The smaller the degrees of freedom, the flatter the shape of the distribution, and resulting in bigger areas in the tails of the distribution. As the degrees of freedom increase, the T distribution approaches the standard normal distribution. And a standard normal distribution is just a special case of a T distribution. That's when the degrees of freedom is equal to positive infinity. For practical purposes, the T distribution approaches the standard normal distribution really quickly. When the degrees of freedom is 30, the two are almost identical. Now let's test what we just learned. I found those items from onlinestatbook.com, and this graph is for question number 1. You can pause the video and take your time, and when you resume it, you can see the answers. So for question 1, which distribution is a T distribution? And the answer is the blue distribution is a T distribution because T distribution has a thicker tails than the red distribution. Question 2. In order to contain 95% of the distribution, you have to go out further from the mean for a T distribution is the answer. Because the T distribution is flatter than the normal distribution. So it has a thicker tails, and the middle part is lower, so it has less scores here, but more scores on the tails. So you have to go out further to contain this 95% of the distribution. Question 3. The difference between the T and a normal distribution is greater with 3 degrees of freedom than with 50 degrees of freedom. And the answer is true. Because as the degrees of freedom increases, the blue distribution will approximate the red distribution. And as the degrees of freedom decreases, the blue distribution will be flatter and it will be more different from the red distribution. We'll quickly go through the 4 steps in one sample t-test because the process is similar to z-test. So the background story goes like this. The healthy general population's social functioning score is 77.43. And a sample of 18 relatives of OCD patients scored a mean of 62 in social functioning, and we set the significance level at 0.05. The first step is to state the hypothesis. As a researcher, I'm biased already. I want to see significant differences. So my alternative hypothesis is the OCD patient's family scores differently than general population. And the null hypothesis is the opposite of alternative hypothesis. So it states like OCD's patients' family scores the same as the general population. And in the textbook, they only used mu, and I put OCD in there because I want to distinguish this one from the original, the general population mean. So step 2 is to set the criteria for a decision. And we use the table on page 481 to find the critical value of or cutoff value for our decision. So the degrees of freedom is n-1 and it's 17. So it's the second row from the bottom in the table. And you go to the top third row, the proportion in two tails combined and use the 0.05 column to find the critical value is 2.110. So the critical value in the right tail is 2.110. And the table only provides a positive values, but we know the distribution is symmetrical. So the left tail's cutoff value, the critical value, is minus 2.110. And the pink area is our rejection region. In step 3, we compute the t statistic to compute the test statistic. We have the 18 scores, so use the 18 scores, we get the mean and we get the sum of squares, and then calculated the standard deviation of the sample, and use the standard deviation to estimate the standard error of the mean, and then use this to get the t statistic, the obtained t value, and which is minus 3.126. And we know this value falls into the left rejection region. And in step 4, we make a decision. We reject the null hypothesis and say, and there is a significant difference between the OCD family's social functioning score from the general population's score. And since we reject the null hypothesis and conclude that there is a significant effect between the sample mean and the population mean, and it's time to compute the effect size. The 3 methods of computing effect size for one sample t-test are all straightforward. For Cohen's d, we used a sample standard deviation instead of a population standard deviation, so it's called estimated Cohen's d. And eta squared and omega squared are measures to estimate the proportion of a variance, which is calculated by dividing variability explained and divided by total variability. Social functioning score is a dependent variable in our example, and apparently the researchers considered there is a relationship between being OCD patient's family and a social functioning score. So being OCD patient's family is a unique characteristic of this sample, and we're interested in how much difference in social functioning score can be explained by being an OCD patient's family. So that's the numerator, that's variability explained, being OCD patient's family. And keep in mind, in both formulas, the t is the t statistic, not the critical value. So the t are obtained t statistic, obtained t value. And the effect size of our examples are, for the Cohen's d, it's minus 0.74. So the negative means it's below mean, the population mean. And the eta square is 36%, and omega square is 33%. From the 18 social functioning scores, we can compute the sample mean, which is 62. And this sample statistic is the point estimate of the population parameter, the population mean. And the problem of using the point estimate is that we cannot tell how close the sample mean is to the population mean. Sample mean is an unbiased estimator on average, but 62 can be too large or too small. So the solution for this is to use interval estimate, which is often reported as confidence interval. We set the critical values at 2.11 and minus 2.11, and want to find out the scores at these 2 points because the population mean has a 95% of probability to fall in between these two numbers, these two values. The t-statistic between the critical values can be stated this way. T is larger than minus 2.11 and smaller than 2.11. And we can use the t-statistic formula to help find the interval. Okay, so t is larger than minus 2.11 and smaller than 2.11. And we put all the numbers in there. All the known, we know the sample mean and the estimated standard error. And to get rid of this denominator, we time 4.94 and to get rid of this denominator. And in this step, we want to get rid of this negative between mu, so we times everything with a minus 1. So we just change the direction. And then we come up with the two values at those two corresponding to the t critical values, which is 51.58 and 72.42. So now we know the confidence interval is 51.58 to 72.42, and that's our confidence interval. And the population mean stated in the null hypothesis is 77.43, and it's outside our confidence interval, so we reject the null hypothesis and state that the OCD patient's family score is significantly different from the general population. And here we use the interval estimate. So the way to calculate the effect size is to use this population mean minus this upper limit, and we get the upper limit of the interval of the effect size. And use this population mean minus the lower limit of the interval and to get the lower limit of the effect size. So our effect size is an interval as well. The basic experimental situation for using the t-test and the z-test is like this. It is assumed that the parameter of population mean is known for the population before treatment. And in our example, it's a 77.43. That's the social functioning score of the general population. And the purpose of the experiment is to determine whether the treatment has an effect. And the population after the treatment has unknown values for the mean and the variance. So we'll use a sample from this population to test a hypothesis about the population mean. If the population variance is known, we use the population formula for z-test. If the population variance is unknown and the sample size is larger than 30, we use the sample formula for z-test. If the population variance is unknown and the sample size is smaller than 30, we use t-test. To use t-test, there are three assumptions: normality, random sampling, and independence. Not all distributions are normal. There are tests for normality and also alternative tests for non-normal distributions, but they are beyond our course, so we don't need to worry about it yet.